Uh, Good afternoon on a Saturday afternoon. So lovely to see you guys. My name is Asif. I work at Amazon Web Services as a cloud architect, and I happened to build the first AI application to be put on containers earlier this year on the ECS platform. So that's why I get to talk about it. In this presentation, for the next 30 minutes, I'll show you how to write an AI application, take an AI application which is built, and then go through the deployment pipeline and quickly ship it, and what are those challenges that we need to work around, and I'll show you a demo also. So when we talk about machine learning, it's not a new term. AI has been there. What has happened in the last 10 years is because of the availability of compute resources and cloud resources, it's become super easy to experiment, to create those models, train those models, and deep learning has really picked up. There are four broad categories of deep learning that people are focused on today. One is image understanding. If you take me a picture, like when you go into check-in for an airport for your flight, for JetBlue, for example, you can now stand in front of that kiosk and it'll recognize your face using facial recognition, and which is using deep learning at the back end, and it'll show you that, hey, this is Asif, check him in. Cool. And so it's already here. There are other parts of deep learning which, for example, if you've used Alexa or any of those home assistants, it uses natural language processing, speech to text, text to speech, and so on and so forth. And everybody's talked about autonomous cars, and some of that is already there. Where is deep learning today? Deep learning today is in our lives before we realize it. So there are applications where, for example, deep learning is being used to help us make choices, give us recommendations, and based on patterns and behaviors. So when you look at Alexa, one of the examples I really like to talk about, is Amazon Go. Amazon Go is a cashierless or cashless kind of a grocery store experiment. It's in Seattle only, I think, but it's a great experience. You go in, you pick up your grocery, and you move on, and you walk out without lines, without taking out your wallet, and your bill comes back on your Amazon account, and it's fairly correct. And you can dispute it, not dispute it, and a lot of that is powered by deep learning. So that being said, we'll talk about where all deep learning is as we move on. But let's talk about how do you build these applications. Building algorithms is great. We will have more and more algorithms coming out. But to make it really tangible and usable, I need to build application and be able to deploy them super fast. So I'm going to talk about this life cycle, or the circle of ML life, machine learning life. So I've on the bottom half of the screen, I've got my machine learning or data scientist folks who are crunching large amounts of data, and they're coming up with algorithms, they are coming up with models, and they build the best model, it's consumable, they've published it. Now, that's just the data engineering part of life. What about the application engineers? And it's almost Greek and French conversation right now, and that's where we are, and we are improving as we go. So there is a DevOps team whose job is to take this code from 0 to 100 and make it repeatable and make it deliver code really fast. The front end or the application engineer's focus is the customer experience, the business logic. For example, when you look at home estimates from Zillow or Redfin, we don't inherently think as consumers, what is the algorithm running? What is the accuracy of the algorithm? How did it get there? We are looking for the experience, the customer experience. Hey, I want the home estimate, and it should be accurate, and I should just quickly be able to get it. There's a whole bunch of engineers focused on that. And DevOps kind of tries to bridge this gap, but today there's a divide which exists. On one side, there are great ML models. On the other side, the question being asked is, how do I really use this? How do I scale this? If I have to deploy it to 1 million consumers and call these APIs, how do I really make this happen? this shouldn't be new for anybody, but DevOps practices have existed for quite a few years, but it's really about continuously building code, like when Git came out in 2008 with small commits, frequent commits, make sure your code works, and when Docker came out in 2013, they made this very repeatable. Packaging was super simple. Now you can take the same image and deploy on your laptop, to your staging, to your dev, and to your production. And that's the DevOps focus, that hey, we want to get this going, get this fast, get this efficient. So there are many benefits of DevOps, but this slide is very abstract because automation is the key of DevOps, like the key soul of DevOps. I could write my script and try to run it, but it's not as efficient if I can build a build pipeline or a dev workflow pipeline. So when the public cloud came out in AWS came out with 2006 with EC2. Before that, the world was, I remember the world where we used to write scripts. Each of us were writing scripts and making them work, and at the lowest level of Linux. But with infrastructure as code, all that became easy. I could define it in a simple YAML or a JSON file and push it, and my resources are ready. I don't have to wait for somebody to give me a box or things like that. Now, things have further moved on, where, for example, with Docker's advent, and how many of us have heard of container management platforms like Mesos, Kubernetes, ECS? Cool, everybody, cool, I love this cloud. So that's a next level of efficiency we are gaining as we go on. And I'll talk a little bit about Kubernetes, ECS and other things. So let's put this together. What are the ingredients I need to build an AI application and go from there? So at the deepest level, you'll have to make a choice, or your data scientist will make a choice of saying, which is the engine I want to use? Do I want to use TensorFlow? Do I need to use Apache MXNet? What is that deep learning framework I want to use to build my models? And that's a whole different set of people. But there are other ways of doing deep learning also. For example, there are AI platforms that exist today. Spark ML is a great example that you can build your models very quickly. And the highest level of abstraction, you have also these managed services that consumers are coming out with. For example, in Amazon, there's Amazon Lex and Poly and recognition. With recognition, you can call an endpoint. You don't need to have the data engineering and the data science expertise in-house. You can call an endpoint, drop a photo, and get back the result. What is this? It gives you 8 different facets of emotions and things like that. So the world has progressed very fast, and these things are becoming available for developers to use. I'm gonna don't go by this picture, but I'm going to focus on deploying this on containers, using containers as a way to get this agility going, deploying it very fast. So going back into Maven packaging, how many of you have used Maven or Java developers? Okay, some of you. So you know Maven. So Maven was great when it launched. The POM file, we could define the dependencies, but very quickly it went sideways, where I remember we had a private Maven repository, and for a library I had a major version but not the minor version, so I had to go through that pain of going to my ops guy and saying, can you please give me that, can you please give me access, and Maven kind of, it did certain things well, but the packaging was not solved like what it tried to solve. Docker came along and did a phenomenal job of helping us package solutions in a repeatable way. The bits were all together, the application, the OS runtime, the dependencies are all packaged together, so I don't have to worry about what's on my laptop, what's on the machine there, and go on. As Docker came along, Docker made running containers super simple on my laptop, where I could just say Docker run and works. And Docker relies on C groups and user namespaces under the hood with Linux kernels, for example. But running it once is easy. But imagine running 10,000 containers. So you've got n containers on m nodes. So you've got an O of n squared problem very quickly. And that's hard cluster management problem. That's a cloud scale problem. And that's where Kubernetes came out last year. Amazon released ECS in 2015, I believe, way before Kubernetes existed. There were other flavors of that. At the time, only Mesos existed. But at the core of it is you need a cluster management service. So what it means is, if I want to be able to reliably deploy my application on containers n number of times, and get that same SLA back, that it doesn't fail. If it fails, it comes back up, and all the benefits that the containers provide me. So at the core of this solution is the managed service, which is basically the brains of it, which says the cluster management, and it does the scheduler and all that. You are deploying your containers on a VM, like on a Linux OS, and that has a bunch of containers deployed together in a construct called a task. In Kubernetes world, it's called pod. So think of it as interchangeable. And these tasks, then you can schedule, and on each of these nodes, there's an agent, which is a thin wrapper on the Docker agent, which helps us talk back to the managed service or the cluster management thing. In the front of this, there are load balancers, and you can absorb that traffic. The load balancer is a shock absorber. So we have, and apologies because of the text broken, but we have looked at all the different pieces, and we know how to scale this solution and how to make this work, but it's still a broken world. How does a data scientist talk to a apps engineer, to a DevOps engineer, and how do I make this repeatable and super fast? So when you look at this picture, a data scientist lives in this world. He has his Jupyter notebook, and there are AMIs that you can launch, and the Jupyter notebook is there, and you can play with it. We believe, and earlier this year we published this blog, is we can use an object store as a communication model. What that means is I build my model and I store it on an object store like S3 or something else where I can store with high durability. And as I'm doing my data crunching and building new models, I'm uploading them to the object store to be available to everybody else. While that is happening, at the same time, my app engineer at the top puts code, commits code, and the nirvana for me as an app engineer, I've been an app developer all my life, is I push code and things just happen. Like this whole thing should be transparent to me, but that's a lot of work that ops need to put in place. So you push your code into a code repository like GitHub. A Jenkins pipeline triggers that. It triggers a Jenkins pipeline. The pipeline picks up that code, builds it on a Jenkins build server or a code build server, and then you can push it to an image repository. In this case, it's Amazon ECR, which is a private image repository, unlike Docker Hub, which is public. You have other repositories like Quay also that you should look at. Once my image is available here, using CloudFormation, and I'll show you that, you can provision a whole cluster of container-based cluster, like VPCs, your networking stack, your task definition, your service, just like that, using infrastructure as code. And if you put this in auto-scaling, which means I tell it, run 10 copies of it. That's all I have to do at the task definition level. It will run 10 copies of it, given the constraints I've given it, and I'll talk about some of them. The cluster manager will pick up the image and start deploying it to those many copies as long as the image is available. So this is a lot of backend that was just set up in no time. Now, the mobile developer, I talked about Zillow as an app or Redfin as an app. That's the focus there. And the guy is saying, this is an image of the Golden Gate Bridge. Tell me what it is. And deep learning, think of it as a image classification as children looking at things. If you go to a child and show him a new picture and ask him what it is, the chances are he's going to relate back to what he knew or similar things he knew, and he's going to do that probability and come back. It looks like this. You know, what is this? It looks like a television. That's basically deep learning, how like we are just doing it on computer except in our brains now. So, and then the picture goes into a DNS endpoint, because you need to be able to, from a mobile app, you need a friendly name to go and hit. So you go to myproduct.com, the DNS redirects you to a load balancer as a shock absorber, and as your traffic scales, and it goes to containers with dynamic port mapping, and your container serves your traffic or runs your machine learning algorithm. And then you can have metrics pushed out to a monitoring tool like Datadog or CloudWatch and things like that. But when you look at this complete picture, what have we just done? We have built a communication mechanism for different parts of my engineering org. So I have data scientists who can upload the model. I have backend engineers who actually deployed, or DevOps engineer who built the pipeline. My backend engineer wrote the code, and in the code, he wrote, pick it up from this bucket in Amazon S3 that pick up the model every time. So every time a new container runs, a new model is getting pulled, and you're getting the latest deep learning model behind it. So with that, I want to jump on to a demo. I want to show you this working, and I think I'm doing fine on time. So this is an open source library. We open sourced like a project earlier this year, and everything I've talked to you about is basically this architecture. You can clone it, you can run it, and things like that. So I'm going to show you how to run this. I'll cheat a little bit on this demo because otherwise this takes a while. So I already have a stack up in US East 1, which is basically I want to serve my East Coast traffic from that region on the cloud. So I would say, okay, let's do this. But let me launch a new stack while we are here, and I'll walk you through the different pieces. So what am I giving the system? I'm putting it a script. I think of it as a CloudFormation JSON file, that a template that AWS understands. There could be a templates for other cloud providers, but this is what AWS understands. And this template, as I go through, and I can say this is called MXNet scale, and I'm going to take the defaults, give it permissions to create stuff, and so on and so forth. So what you see here is really, and when it really kicks in, you'll see multiple stacks getting created, and I'm not sure if you can read it at the back, so let me go zoom. So what am I creating? I'm creating my networking stack and all the networking parameters, all of my cloud infrastructure at the click of a button, as long as I've coded this well. I'm creating my build pipeline through this, and I'm going to also build this. While that is happening, let's switch over to something which is pre-baked. So I've created my VPC, my networking stack. I've created my build server, build pipeline. I've created my ECS or container orchestration mechanism, the nodes, the task definition, the service definition, the load balancer, all of that I'm creating. So let's dive deep and understand what is really happening. So let's look at the code as a starting point. So I have my code which is called image classification predict, and when this comes up, so there are two files in this. One is a build spec YAML and a Docker file. So let us look at the Docker file first. So what am I doing at the Docker file? I'm basically installing an MXNet library in the container because I need that framework to be able to do inference. So this is really using the inference. I'm not doing training. I'm assuming the training is available. And I'm basically saying launch my Python app, which is my application. I also have a build spec YAML. The build spec YAML tells the build server what are those steps you need to execute. So it basically builds a Docker image, it gets the login to the repository, and then pushes and tags the image. Going back into what the app is doing, so let's go back and look at our Python code. So the app is basically saying, when I hit this URL at /image, go and get the params and then predict what it is. And the predict basically works by saying it's an array, an NumPy array in MXNet, and I'm basically asking it, hey, what is it that you're doing? Give me the result, and then I'm kind of outputting that the probability is this so that I can read from it. That's all the code I wrote. That's literally machine learning code I wrote, like using MXNet as a framework. But I need the framework to be able to run this in containers n number of times. So I've written my code, I've tested it, I believe it works. Now let's go look at the DevOps code, the pipeline that got set up. So this is a very simplistic pipeline. You guys have done Jenkins. This should look very similar. This is a code pipeline. But it pulls code from code commit that I showed you, and then it basically builds a code on a build server, the managed build server. And it basically provisions the environment. You can pick the environment and things like that. And then it basically runs all those Docker commands and builds the Docker image, like all of this. And finally, it pushes it to the image repository that I talked about or showed you. Let's look at what got pushed to the image repository. So when we go to the image repository, I have a image rep. Okay, I lost the screen. Okay, okay. So this is like a private image repository, like like your own Docker hub, living in your security constructs of your own organization. And what I've pushed is the bits, and I've called it latest. I can also assign it permissions, who can push, who cannot push, and things like that. So if I say Asif, I can say Asif is a principal, and he can only push pull. Then he can do only these activities on the image repository. So this is super important when you're designing systems to be production ready. So that's great. Let's look at the cluster that we just created. So in this case, the cluster is called MXNet ECS, that random string. And okay, this is sensitive. I have in the cluster, I have one container node, because I'm using, like, I'm not running a massive cluster, and I've picked up, okay, I need to do something about this. And I'm using the Docker as a runtime engine and things just out of the box. I have a service, and as I explained to you, a service is basically a way to multiplex down to the containers, and then I have a target group. So when Docker gives you different bridge modes, networking modes, host, bridge, and things like that. The physical port, if you go in the host mode, you can use only once, 8080, and you're done. So there is a concept of dynamic port mapping that you can use to multiplex an 80 on the load balancer to some random port on the on the EC2 instance. Okay, let me try this. Yeah, it's just a little sensitive, that's it. Yeah. So behind the service lives a task. Think of tasks as a pod spec in Kubernetes world, for example. So to the task, I'm saying what are my host port. My host port is the random port that I talked about, 32769. My container port is 5000, but my load balancer is 80. So I can hit this API at 80. And then I also have integrations to my monitoring. So I can go back and show you all the logs that this application or the containers are generating. We'll go back, it's mostly 200, so it's not causing any errors right now, which is great. And then I can configure all this, and the image that I have, as you can see, I'm pulling from my ML test repo. I've given it 4 CPUs. This is super important to know. So with MXNet, one of the things you can do is you can train your model in GPU, but run your prediction in CPU. So that's why you see me using a CPU machine. So think of that when you're running your deep learning applications. So if you have a your training is running on GPU, you need those cores, but you can always run your inference on CPUs. So I've given it 4 CPUs to run each container gets 4 CPUs at the max. And I would also put a hard limit on memory of saying you should not use more than 3 gigs of memory, and otherwise you're just killing the system and you're not being a good citizen on the node. And it's essential. If this doesn't come up, it fails. So with all of that, and we'll see how far we went here, and something failed there and you can see that very quickly. That's one of the buckets was not created or was there, and it kind of threw up on me, but that's okay. So if I go back now and I look at my master stack and look at the output, I get an API, a URL, a very friendly URL that I can use with my mobile application, my front-end applications very quickly. I'm going to show you that with Postman. And it comes back and says it's a suspension bridge with a probability of 62%, which is pretty cool. Imagine building a deep learning application in 15 minutes or 20 minutes, and you have an endpoint. The agility it gives you as application developers, the front end, the back-end engineer, and the communication it enables. We can go down into the bucket and see the model if that's of interest. But going back to the architecture or the system architecture that existed, and yeah, it comes up. So what we have just seen in the last 10 minutes of demo is basically, as a data scientist, as an application engineer, as a mobile engineer, as a DevOps engineer, all of this can work in harmony and has to work in harmony to deliver really consumable and really nice customer experiences. Like when we look at the Zillow app and say the estimate is it's 800K, there's a lot of engineering and the pipeline that went through. Let's say during that process, one of the data scientists came up with a new model. The change is very simple. It's an upload. Nothing else changes. It's just I trained my system on my cluster and I uploaded the image. Similarly, if I change my application front end, the mobile client basically updates, goes through the same pipeline and deploys without impacting anybody else. And that's what containers kind of give you that demarcation and agility for. So that's all I had to present. I wanted to leave some time for Q&A at the end. So I hope you drive something out of this. How many of you knew this before, from before I started? Okay, you knew this, nice. So you're probably building an AI platform already. So you said you knew this from before. Yeah. So exactly. So a lot of AI platforms that are getting built, just as an annotation, and startups, large companies. We publish this blog, and maybe I should also give you the link. And this will be available. It's a 404. Good one. Let me copy this. It was the wrong click. So, and there's a space in between. That's what is the problem. So this is basically the whole talk that I gave you is we built the project, we open sourced it, we wrote a blog to make it repeatable, and all of this is there for you to try. Like you can go through the code, what we did, and this is how a model looks like under the hood. Basically, you're defining nodes, and you're saying, hey, it's a convolutional network, CNN, and what are the different parameters, and it's basically the math that it understands. And the back end of this, the whole predict part of it is already open sourced. So hopefully you can go back and take a look at this, give us comments, maybe do a pull request on the GitHub repository and let us know how the thing is. If things don't work, raise an issue, we'll take a look at it and fix it. But a lot of the conversation around AI platform, people who are trying to build AI platforms are building it kind of in this same genre, not exactly doing the exact same steps, but different people are doing different steps. But this is what the problem needs to be to get solved, right? So with that, I'll take a pause and see if there are any questions that I could answer. There's a question in the back.
Google has these TPUs which are faster than GPUs, and I was wondering whether the Amazon, AWS, whether they're going to have something like that.
So I'm not sure if you caught the thing. There was Volta, NVIDIA Volta, that was announced, like the support for that was announced. So I would say take a look at that. But as compute gets faster, so the new classes of instances coming up all the time from Amazon, and similarly other people are trying to bring up other instance types. But I think when you're building platforms, TPUs or GPUs are super important when the training part of it. But when you're running it on the inference side of it, you need to take a step back and say, do you want to run it on, what is your use case you're trying to solve? We always try to think that we start from the customer experience and say, if I can do that on CPUs and get a performance that I want, why should I spend more? So optimize your architecture for cost, security, operational efficiency, and then things like that we normally call well architected. Does that answer your question? Okay, thank you. Any other question? Okay.
So how much does this cost? If I did this AWS, how much will it bill me?
How much will this bill you?
Yeah, if I did this on my own.
So I'll tell you the cost. So let me go back to the picture. So you don't pay anything for ECS. ECS is free, okay? You don't pay anything from devreal, of course. You pay for storage. In the cloud, you pay for two things, storage and compute, right? So all the nodes that are using, they'll be billed by the seconds. So I'm running a pretty large P2 kind of a GPU cluster, so it's gonna cost me a little bit. But you have the choice of taking the instance type that you need, and there's a free tier that you could use, and it bills you by the cents or things like that. But the curve, and I showed you that in the picture, was compute is getting cheaper. We have cut prices like above 55, like the last count was 56 a year ago. I think we are way higher than that. the cost is it's basically the Moore's law, right? And deep learning is able to use that. Your cost of running deep learning algorithms or training is become so cheap and so affordable, inexpensive, that you could actually run a whole model training and pay few dollars, few $100 and get away. And then a lot of this that you saw is free. Like you pay, for example, if you look at code build, one of the biggest sacrileges I've seen out there is Jenkins running on a node and running build for 2 hours a day, but you're paying for the whole day. A managed environment, you pay by the minute. You pay only for the time, the compute cycles you use. So when you look at these architectures and see the efficiencies it gives you from cost, from speed, and all of that, that gives you, and in fact, S3, there are different storages in S3 that you could use. So when you put all of that together from the platform perspective, and there are other platforms that you could use, not just Amazon, I think the cloud in general has become, has made things affordable, inexpensive, and you can do these experiments very fast and build. You know, we tend to say that builders should build and the rest should not be an impedance, right? So think of it like that. If you want a real number, there's a simple calculator on Amazon. So you can put in those instance types and storage and you will get the number out.
In your example, did you have costs?
I haven't measured the cost honestly, but I have not paid. I run tons of things, but I don't see a bill even on the hundreds. So, and Amazon pays for it, so I don't. Okay. Anybody else? Any questions? Cool. There you go.
Yeah. Where you can get more resources about just looking at this whole thing besides the blog post that you put? Like, you know, are there more links where you can see more of these things in detail and just...
Yeah, so the GitHub project is definitely, the blog is a starting point. The next thing I would do is take a look at the GitHub project. Basically, if I can go to the GitHub project, it should, yeah, this is the GitHub project. I would start here, and I was pleasantly surprised when customers started using it and they would ask me it's working or it's not working, and we would add to it or remove from it, and they would fork it and do their own things. This is a good start. You can also go to the AI site. On our site, deep learning, we have a whole microsite called deep learning, and you can learn this. Similarly, on the container side, if you go and say ECS resources, you will find a lot of documentation, white papers, what other people are doing with containers, and so on and so forth. And you will also see the blogs and the reference architectures that we talked about here. How do you build pipelines and things like that. And similarly, if you like, it's as simple as searching for deep learning, and it gives you the deep learning AMI. So if you want to do the training on Jupyter, you could basically launch the deep learning AMI, the Amazon machine learning, click, and it launches your environment, and you have a ready to go Jupyter instance. Like literally you can start using with TensorFlow, with MXNet, whatever you want to use, and so on and so forth. So I would say these are the starting points you should go back to and take a look, but start from the blog, go to the GitHub repo, then start digging deeper. And if you issue a pull request, I'll be the happiest guy in the room. Thank you. Okay. Cool. Thank you for listening to me. Thanks for your time. I hope this was valuable.